Again, today we are starting a new unit, Unit 3, which is about circular motion and universal gravitation. Kind of two pieces. They sort of fit together, but they're not enough to be two separate units. Today we're going to start talking about circular motion. Some of these words should be familiar: tangential and angular motions. Again, we're going to dive into what those mean. First thing, you guys should have a basic understanding of what rotation is. Rotation specifically is spinning when your axis is located within your object. It rotates about some axis within itself, right? For example, this ball, you could also think of the Earth. The Earth rotates. The axis about which it spins goes right through the middle of the Earth, so it rotates about an axis within itself. The other word that you see, revolution, is rotation that happens, or spin, where the axis is outside of the object. The Earth is another good example. Not only does it rotate about its own axis, it also revolves around the sun. That axis that it revolves around goes through the middle of the sun, and that axis is outside of the object itself. So in this case, you could imagine if that soccer ball were the Earth, it would be rotating around the sun, and that's called a revolution. Earth rotation, the time it takes to complete one rotation, when we calculate that time, it's called a period. So the period of rotation, capital T, for Earth is just shy of 24 hours. Now the revolution, the period of revolution, we also call T, that is the time it takes for Earth to rotate, or rather revolve, around the sun. That period, or time it takes, is 365 days. Technically a little bit over. This is why we have leap years. Every 4 years we lose a day because we've had a quarter of a day extra every single year. Again, we use this idea as a fundamental way of how we go through life. What we call a day, a 24-hour period, is because it takes 24 hours for the Earth to complete one rotation and start from where it began. Right? 24 hours that Earth was able to rotate one complete rotation. Now here you can see as the Earth rotates about its own axis, it's also revolving. It's revolving around the sun, right? The Earth is in its orbit. It is revolving around the sun. So when we start looking at circular motion, when we look at motion in a circle, we measure it using degrees. Now you've likely seen this. You've maybe used a compass. You talk about 23 degrees north, northeast, things like that. When we talk about a degree, we're talking about 1/360th of a rotation. When we say a degree, we're talking about a certain fraction of a complete revolution. You guys might know there's 360 degrees in one full circle. Same way that we measure distance in feet, we measure rotation in degrees. There's also something called a radian. A radian is a unique dimension, a unit of measure, that's defined as any angle where the arc equals the radius. Now to show you, this purple line is the radius. It's the distance from the center of a circle out to the edge of the circle. A circle has a constant radius no matter what point on the circle. That's the definition of a circle. The arc is the arc length. So we just saw motion happen where it covered a certain amount of rotation. This blue line represents the arc length, the distance that this point traveled along the circle's edge. A radian is whatever angle measure produces the same arc length that's equal to the radius of that circle. So if you travel 1 radian, you know that the arc length, the distance you traveled on the edge of the circle, is equal to the radius of that circle. In this case, 53 or 57.3 degrees for a circle. Again, we just mentioned this is the definition of a radian. If you move half a radian, the arc length that you've traveled is half of 1 radius, the radius of the circle. If you move 2 radians on a circle, that means that this arc length that you've traveled is 2 times the distance of the radius of the circle. So we come up with this equation that says the arc length, the distance you travel along the edge of the circle, is equal to the radius times the number of radians that you've traveled. You might be asking yourself, I know there's 360 degrees in 1 full circle. How many radians are there? There's 1, there's 2, 3, 4, 5, 6, and then a little bit, right? 6 and a bit. When we actually do the math, the circumference of 1 circle is 2 pi r. Right? That's a geometry proof. Well, if I get rid of my dimensions, I'm left with the number of radians in a complete revolution is 2 pi. 1 full rotation is 2 pi, or rather 6.28, etc., radians. If you look at the units, radians, or the radius, is measured in meters. If I have meters divided by meters, I get nothing. This is because radians is the ratio of the arc length to the radius, so it actually does not have any units. Now we need to start talking about, we're looking at circular motion. When we look at the number of degrees or the number of radians, we're essentially talking about displacement. The same way, if I've traveled 5 meters, in circular motion, you're going to say, I've traveled, say, 45 degrees, or I've traveled pi radians, or 2 pi radians. Well, the same way we can look at the velocity of linear displacement, we're going to look at angular velocity. How does my angular position, or my number of degrees or radians, change over time? This is where we introduce, this is the Greek letter omega. Omega is the variable for angular velocity. For example, if you're moving at 90 degrees every second, in 1 second you will have traveled 90 degrees. So to travel a full 360 degrees, it took you 4 seconds, because you could do 90 degrees every second. Here's our formula. Same way that velocity equals displacement over time, angular velocity equals angular displacement over time. Now what happens if I have a slower angular velocity? Well, I rotate slower. Should make a lot of sense. The period, capital T, the time it takes for 1 complete rotation is 6 seconds, because in 6 seconds I can cover 360 degrees, which is the definition of 1 full rotation. If I move 1 radian per second, how long does it take me to complete 1 rotation? Well, I know that there is approximately 6.28 radians every second, or radians, in a full rotation. So it's 6.28 seconds. Again, these are the same thing. They're just 2 ways to measure angular displacement. If I move twice as fast, I can cover the same displacement, in half the time. This is a term you might see, secant. That's where a line intersects a circle at 2 points. If I come out here, this is called tangent. A tangent line is where the line touches the circle at only 1 point. Imagine you have this line and you just barely touch the circle. As soon as that happens, you have a tangent line. One thing we can look at is if we have an object in a circular motion, if we let it go, it would travel a certain distance. This is a linear displacement. We've done this. But it doesn't travel in a straight line, it travels in a curved line. Well, we can compare the distance of this curved line to the distance of this straight line. This is showing you if I took this distance traveled along the circle, this arc length, and bent it into a straight line, it would equal a linear displacement. So if we have the angular velocity, how much the angular position changes with time, we could also relate it to just linear motion, which is just distance over time. Well, our distance is actually the arc length, radius times the angle traveled, divided by time. This is where we get delta theta over t. This is the equation where we can relate the angular velocity, how your angular position changes with time, and relate it to a linear displacement, or linear velocity, our regular v for velocity. If I multiply the angular velocity by the radius, it would tell me the linear speed of that car. So this car is traveling at a speed of 40, say, miles per hour. If you notice, watch this again. This car is traveling at 40, say, miles per hour. At this point, if we imagine the car travels at the same speed, in a linear direction, it would cover 40 meters linearly. Since it's an angular motion, it covers 40 miles in 1 hour in an angular displacement. Same thing is true if we look at the acceleration, how the linear velocity changes with time. We can have something called an angular acceleration. How does my angular velocity change with time? In this example, you'll notice my angular velocity is increasing. I have some angular acceleration. Now if we look at, again, a car's motion, acceleration is a change in velocity over time. Well, the change in angular velocity over time is angular acceleration. So again, when we calculate the radius times the angular acceleration, it would tell us how fast it's accelerating linearly. We have a car that's speeding up. It got up to 40 miles an hour, but it accelerated along that path. These should look very familiar. These are equations we've used for kinematics, investigating the motion of objects in linear directions. Well, there's actually no real difference between the motions that govern circular motion. Right? The equations that govern circular motion are identical, but we have to use circular or angular variables. The velocity is the initial velocity plus the acceleration over time, or times time. The same equation holds true in the circular motion. The angular velocity equals the initial angular velocity plus the angular acceleration times time. Displacement linearly, as we measure in meters, as x. Well, displacement in circular motion is how many degrees or radians you are displaced. angular velocity, angular acceleration. Same thing down here. We replace velocity with angular velocity, acceleration with angular acceleration, displacement with angular displacement. Again, I want to remind you that the velocity of something is equal to 2 pi times the radius of motion divided by the period. If you look at these objects, you can see that they have the same angular velocity, right? Let's look at them starting here. It takes them all an equal amount of time to cover the same angular displacement to get one full revolution. That means they have the same angular velocity. However, the radius, I think it's calculating the inner to outer, the radius is different. Well, in order for them to travel at the same angular displacement, they have to have different velocities, rather tangential velocities. If these are cars, this car is traveling, say, at 10 miles an hour. This car is traveling maybe 20 miles an hour, and the blue car would be traveling 30 miles an hour. In this case, comparing one to the other, it's about twice the tangential velocity. If you have a record, the edge of your record is actually moving the fastest because it's keeping pace with the rest of the record, but it has to move in a bigger circle, so it has to be moving faster. Again, if you follow these points along these two different radius circles, notice they have the same angular velocity. They travel the same angle the whole time. But then if you look here, this focuses and highlights the linear velocity. The top, we see that each particle is moving faster than on the inside loop. That's because to keep moving at the same angular pace, it has to cover more distance, so its actual speed is bigger. Now this one's tricky. When you look at it, all three of these cars are moving at the same speed. They would all be set at, say, 20 miles an hour. They look different because they're traveling on different sized circles. Their actual linear velocity, the speed that they're traveling, is the same, but the radius is a lot bigger. So the total angular velocity, how quickly it can complete one rotation, is decreased as I go to a bigger circle. This is why on a track, which runner has the greatest advantage? Well, if you look here, if they all traveled the same speed, the inside track would get around in the least amount of time. So if all runners could run the same speed, the inside track would win. This is why when they start track races, they start them at different positions. The runner on the very outside starts the furthest ahead because they have an advantage, or a disadvantage, because they have to run a larger loop. So they get a head start to make everything fair. And in this situation, they all are traveling on the same radius, the same circular path. You'll notice that they all have different speeds. Some are moving faster than the other. Well, since they're all on the same linear or circular path, their tangential velocity and angular velocity are the same, except one is bigger than the other car or ball, showing that if you have the same radius, a larger tangential velocity, right, the speed that that car, say, is traveling, results in a larger angular velocity, since the radius is held constant. This is why race cars, they almost always drive in a line. They all want the inside line, which is the shortest distance. That way it's only down to which car is the fastest, or who can maneuver their car the fastest in order to get around the racetrack. And I think I'm going to pause it there. We'll continue these slides when we get back, which would be on Tuesday. I'll discuss the rest of these. Again, reminder, in class today we're finishing worksheet 3A and 3B. Do those to the best of your ability. They should be fairly straightforward. I will go back and point out a hint. In order for these objects, we'll do a slow one. In order for these objects to stay in a circular motion, you should be able to realize I need some sort of acceleration. Even though these are moving at a constant velocity, which means there's no acceleration, they're turning. Well, I can't have my velocity change direction unless I accelerate. Velocity is a vector. It's got a magnitude and direction. If I change the magnitude, I change my vector, and I need an acceleration to do that. The same thing is true if I want to change the direction of my vector. Remember Newton's first law. An object in motion will stay in motion unless acted upon by an outside force. If I'm changing my motion, aka turning, changing my direction, there has to be an acceleration. The change in motion follows the change of the force or acceleration. If I constantly am turning left, right? Left, 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 left. I constantly have to turn left a little bit in order to remain in a circular motion. That means my acceleration always points left. Well, that means the acceleration always points to the center of the circle. I'm constantly accelerating towards the center of my circle in order to constantly turn left and stay in circular motion. This will be very helpful when you do these worksheets to get an understanding of where the acceleration is happening. Even though it's accelerating, it's not changing its speed. The acceleration is causing a change in direction, which is still acceleration. So hopefully that's helpful. Again, we'll discuss this more when I come back on Tuesday. We'll tie up any loose ends and I'll finish these slides. Thank you guys. Have a great weekend.